In general, the zeta function diverges in the critical strip where s is greater than 0 and less than 1. So the non-trivial zeros of the zeta function are obtained by the eta function that converges in the critical strip. The slider in the function window is the real part, and the x-axis is the same as the imaginary part. Therefore, they are symmetrical to each other with respect to the origin. The blue alternating sum of cosine corresponds to the real part of the eta function, and the red alternating sum of sine corresponds to the imaginary part of the eta function. As real part approaches 1, the positions of their zeros move away from each other, and as real part approaches 0, not only do their zeros move away from each other, but their amplitudes also increase and they diverge in a spiral. The zeros of the blue real part and the red real part coincide at a equals 1/2. If the n terms of the alternating sum are increased, the location of the zeros can be found more accurately, and the non-trivial zeros can be obtained at approximately n equals 100. Just like the eta function, the non-trivial zeros of the odd eta function can be found by odd alternating sums. The green alternating sum of cosine corresponds to the real part of the odd eta function, and the brown alternating sum of sine corresponds to the imaginary part of the odd eta function. As real part approaches 1, the positions of their zeros move away from each other, and as real part approaches 0, not only do their zeros move away from each other, but their amplitudes increase and they diverge in a spiral. At a equals 1/2, the zeros of the green real part and the brown real part coincide. The non-trivial zeros of the odd eta function are also on the critical line. This is the same as the generalized Riemann hypothesis that the non-trivial zeros of the L function are on the critical line. By analytic continuation, the non-trivial zeros of the eta function and the non-trivial zeros of the zeta function are the same on the critical line. However, even if the non-trivial zeros are calculated up to 10 million terms of the eta function, the error range is more than 6 decimal places. Therefore, it is more accurate to find the non-trivial zeros of the zeta function by generalization of Fallhaber's formula.